last several sections, we've run into quite a few different tests for convergence. It can be a little bit overwhelming at times to keep track of all of them. It can also be overwhelming to run into the kind of problems where I give you a series and I don't tell you what test to use, and you start panicking when you realize you don't know which test to apply. So this video is going to be kind of a wrap up to sections 10.2 to 10.5. I'm going to hit most of the tests that we've run into in those sections and give you some pointers for just what to look for knowing what to apply where. Okay, so suppose that you're given some series, the sum over an, and you want to determine convergence. Well, here are some thoughts. Here are some things to keep in mind. The first thing to pay attention to is, well, maybe you have a geometric series or a p-series. So a geometric series is just a constant times r to the n. So you should know that these series, they converge if the absolute value r is less than 1, and they diverge if the absolute value r is greater than or equal to 1. So if you see something like the sum from n from 0 to infinity of 5 times 4/5 raised to the nth power, here we see that r is less than 1 in absolute value, and so this is going to converge. If we see something like n from 0 to infinity of 7 times minus 7/6 to the n, well, here, the r is bigger than 1 in absolute value, and so this is going to diverge. So converge and diverge. The next thing that you should just know instantly is p-series. P-series are going to converge if, so this is the sum of 1 over n to the p. They converge if p is strictly greater than 1. They diverge if p is less than or equal to 1. So 1 over n to the 2.7, this converges because p is 2.7 is bigger than 1, and then the sum of 1 over n to the 0.8, this is going to diverge. So C for converge, D for diverge, C for converge, D for diverge. Okay, so these are some things you should immediately know just off the top of your head. The next thing that you should be thinking about is the nth term divergence test. It's always kind of worthwhile to spend a few seconds on each problem, just do a quick sanity check to see, does the limit of the individual terms of my sequence, do they go to 0? Because if I were to give you something like the sum from n from 0 to infinity of, let's say, n cubed over 3n cubed plus 2n plus 7, something like this here. You could definitely do this with other tests that we'll see later on in the section, but it's a little bit easier to just realize the limit as n goes to infinity of n cubed over 3n cubed plus 2n plus 7, and that's just going to be 1/3, and that's not 0, so this diverges. So it can always be a good little sanity check to do this kind of thing. Another example, I think this was something from a previous worksheet. N from 0 to infinity of cosine of 1 over n. Okay, so the thing to realize here is the limit as n goes to infinity of cosine of 1 over n. 1 over n is going to 0. Cosine of 0 is 1. So that's equal to 1. It's not 0. And so both of these series diverge. But just something to keep in mind, if the limit is, so this only goes in one direction. That if the limit as n goes to infinity of a sub n is not equal to 0, you know your series diverges. If the limit as n goes to infinity an is equal to 0, you don't know whether or not your series converges or diverges. You'll have to go on to one of the other tests that we're about to look at. Okay, so the next thing that I want to talk about has to do with positive series. So most of the series that are coming up here are going to be series with only positive terms. So another good one to think about is if nothing works so far, ask yourself if you can apply the direct comparison the direct comparison test. Can you drop terms in the numerator or denominator to get a series that you can work with? Because you should know that if a larger series converges or a smaller series diverges, the original series will do the same. So as an example of this, let's say you have the sum from 1 to infinity of 1 over n squared plus square root n. So what are we going to do? We're going to drop terms in the numerator and denominator. We're going to drop the square root n. The square root n is less important than the n squared. And so we know that the sum from 1 to infinity of 1 over n squared, this converges. It's a p-series where p is equal to 2. We already talked about that. And we know that 1 over n squared plus square root n is less than or equal to 1 over n squared. So here we are seeing that a larger series converges, so our original series must also converge. Now you have to be careful though, because sometimes you want to drop terms in the numerator or denominator, but sometimes you have the inequality going in the wrong direction. So for example, the sum from 1 to infinity of 1 over n squared minus square root n. Let me start this at 2 here to make sure that we don't have that be undefined at n is equal to 1 here. So again, we could try comparing it, direct comparison test, to the sum from 1 to infinity of 1 over n squared. But we run into a bit of a problem here because the inequality goes in the wrong direction. We're only accomplishing showing that our series is bigger than something that converges. So we're knowing that a smaller series than this one converges. That doesn't tell us one way or another what is going on here. So the direct comparison test doesn't apply. But that doesn't mean we should give up. What it means that we should do is, the next thing to think about is the limit comparison test. So it's a little bit more work to apply the limit comparison test than the direct comparison test. So we should always think about the direct comparison test first, but it behaves by the same principle. So drop terms in the numerator and or denominator, and then compare the original series to the new series. So again, let's be thinking about the sum from n from 2 to infinity of 1 over n squared minus square root n. And again, we're going to be thinking about, so we'll compare a sub n is 1 over n squared minus square root n. B sub n is going to be 1 over n squared. And we know, why do we care about this? The sum of the b sub n's, this converges. We saw that in the previous slide. And so the calculation we have to do now is the limit n goes to infinity of the ratio of a sub n to b sub n. 1 over n squared minus square root n over 1 over n squared. And so this becomes n squared over n squared minus square root n. And I'll just leave this as a Calc 1 exercise to see that, yes, this limit is in fact equal to 1. Okay, so because this limit is equal to 1, it's a positive number, it's bigger than 0, and it's not infinity. So by the limit comparison test, we conclude that this series and this series have the same behavior. So this series, the one that we care about, is also going to converge. So what's the moral story here between the direct comparison test and the limit comparison test? They both operate under the same principle of dropping the less important terms. But the limit comparison test will apply in more cases, but it's a little bit more work to apply. So you should ask yourself if you can just do a direct comparison test to save yourself some work. If not, think about the limit comparison test. Okay, so maybe you don't see how to drop terms to do it, and not everything will be amenable to this kind of test. So some more tests to think about. You can think about the ratio test. So things that should make you think ratio test are factorials and also constants raised to the nth power. So something like 2 to the n, 3 to the n, minus 1/3 to the n. If you see those things, ratio test might be a good idea. So as an example of this, suppose you have the sum from n from 1 to infinity of 3 to the n over n factorial. So if you apply the ratio test here, what are you going to end up with? The limit as n goes to infinity. So note we've got a factorial in the denominator. We've got a constant to the nth power up here. So a sub n plus 1 would be 3 to the n plus 1 divided by n plus 1 factorial. Then a sub n would be 3 to the n over n factorial. And so everything in sight is positive. I'll drop the absolute value bars, and I'll simplify this down to 3 over n plus 1. If you don't see how to do that simplification, work it out yourself. And that is 0, so that is less than 1. So the ratio test tells us, oops, not diverge, it converges. So ratio tests, the things that should make you think ratio tests are going to be factorials and constants raised to the nth power. Root tests, you want to be thinking about things raised to the nth power as well, maybe not just constants, but other things raised to the nth power, or sometimes the power can be some function of n. So the example here, sum from n from 1 to infinity of 2 to the n over n raised to the 2n power. So what does the root test say to compute here? Limit as n goes to infinity, the absolute value a sub n to the 1 over n power. And so we have 2 to the n over n to the 2n raised to the 1 over n power. And so 2 to the n to the 1 over n power, that's just 2. N to the 2n raised to the 1 over n power. So you multiply 2n and 1 over n, and you get n squared. And this is also going to be 0. And so the root test says this is less than 1. So this is going to converge. So what are the things that say root test, root test, root test? Stuff raised to the nth power. Okay, the integral test. Suppose, so this is a little bit more complicated one because you have to do integral. So we're putting it at the end. If you have a decreasing function, and we're assuming everything here is positive, your series converges if and only if the integral of the corresponding function converges. So you should be asking yourself, if you replace n with x, is the resulting function something you can quickly find an antiderivative of? And so, as an example of this, the sum from n from 2 to infinity of 1 over n natural log n. So this would be tricky to do with the other series tests we've looked at. Nothing would really say one way or the other. But this is a decreasing function. It's continuous. Everything is checking out here. And so if we think about the integral from 2 to infinity of x times natural log of x, this is easy to do with u is equal to natural log of x, and du is equal to 1 over x dx. So this would be the integral from natural log of 2 to, I should be replacing this with an r here, and so I can get natural log of r, and say, so the limit as r goes to infinity here of 1 over u du. And I'll say here, it isn't too hard to do the calculations to crunch those out to see that you get infinity here. And so the integral, this improper integral, has the same behavior as this function. So this one diverges. Okay, so that's the integral test. And so that kind of wraps up our test for if our series only have positive terms. Sometimes we'll run into series that are not positive series. So we have the alternating series test. The sum from minus 1 to the n of minus 1 to the n times b sub n. If we have a decreasing sequence that converges to 0, the series converges. So, for example, the sum from n from 1 to infinity of minus 1 to the n, or it could be minus 1 to the n minus 1. Both would be fine there. I'll stick a minus 1 here. And how about n cubed over 4n to the 4th plus 3n squared plus 1 here. So what you'd have to do here is you have to say this is a decreasing function. It converges to 0. And so that would be enough to tell us that this converges. And so final point here, if your series is not alternating, well, maybe you should think about if when you sum the absolute value of a sub n, can you take care of that using previous tests? So maybe one example of that would be the sum from 1 to infinity of cosine of n over n cubed. Now, the cosine n is going to be sometimes positive, sometimes negative. It's going to be kind of complicated, bouncing back and forth. But the thing is, if you think about taking the absolute value here, you can observe that the absolute value of cosine n over n cubed, this is always less than or equal to 1 over n cubed, because cosine n is going to bounce be trapped by minus 1 and 1. And we know from P series that this series converges. So this series converges, so this series converges. We're showing that this absolutely converges. We're using the direct comparison test here. So final resort, try thinking about absolute convergence. Maybe you can do something with it. Okay, so I know that's a lot to go through. This is probably the longest video of the semester. But this does a pretty good job at wrapping up things that we've talked about in the last 4 sections.